Hey everybody, welcome to our first real analysis of algorithms lecture. In this lecture, we're going to talk about the best, worst, and average case complexity of an algorithm. Okay, so before we get to that, let's talk about what we're trying to do here. What is algorithm analysis about? Well, the main thing is what we're trying to do is relate the problem size to the time taken to solve the problem. Okay, so basically, when you're running an algorithm, you're always running it on some data. What we're trying to figure out is, as there's more and more data, how does the time taken to run the algorithm grow? As an example, let's say we have 5 elements, okay? And we know that the algorithm takes X seconds, okay? So for 5 elements, it takes X seconds. If we have 10 elements, how long will it take? An intuitive answer might be to say that it'll take 2x seconds, right? We have twice the inputs, so it might take twice the time. But that's not always the case, right? Let's consider an algorithm that says print out the head of a list. Just print out the first item in the list. If you have a list of 5 items, how long will it take? It'll just take one operation. We'll just print out the first item and forget about it. If you have a list of 1,000,000 items, how long will it take? It'll take the same amount of time. We'll just take the first item and print it out. So it's not necessarily true that the time taken to run the algorithm grows as the data in it grows, right? Similarly, let's say we had an algorithm that had to compare items to each other. Okay, so if we had 5 items, we might have something like, 15 comparisons, I guess, if we were comparing every item to every other item. If we had 10 items, we'd have like 45 comparisons or 55 comparisons. I don't know, something like that. But it would be way more than double, right? Because we're comparing all the items to every other item. So although we have twice the number of items, we can have way more than twice the number of comparisons. Okay. And an example is shown in the graph below there. So we can see that the graph we're trying to draw is of input size versus time. Okay. And we're always, when we're doing these analyses, we're always trying to figure out what this graph looks like for the algorithm that we're analyzing. Okay. Now, we often might get something like the blue line, big O of n, which says that the algorithm's time grows linearly with the input size. So maybe in that case, if we had 5 items and it took X, then 10 items could take 2X because there's a linear growth there, right? But we might also end up with something like the red line, big O of n squared, right? And there we might find that with 5 items, it takes X, but with 10 items, it takes 4X instead of 2X or something like that, right? It grows at a greater rate than what we would expect. We could also get something like the green line, big O of 1. That's like the example I just gave about if you had to print out the first item in a list, if you had to print the head of the list, then no matter how big your input size is, the time taken stays the same. So you end up with a constant graph, right? Look at the green line, it just stays, the time taken just stays the same. Okay. Now, the important thing about this is because what we're trying to do is draw a graph with input size on the x-axis and time on the y-axis, we can't fix n. We can't say, hey, n is 3 or n is 1 or as is the most convenient, n is 0. We can't do that because then we wouldn't end up with a graph. We'd end up with a point, right? We'd end up saying when n is 4, the time taken is 10. And then there's just a dot on the graph and there's no line. For us to have a line, we need to leave n as unconstrained. Obviously, we don't have negative numbers for n because you can't sort -5 items or something, right? There's always a positive n. Okay, now what we talked about there was that we're trying to come up with some relation for how long the algorithm takes to run. Now, that analysis works if the algorithm doesn't have characteristics of input that are going to mess with the runtime. So, in your lab, you had an example where you had to do an algorithm called linear count, where what it would do is it would go through a list counting the number of times a particular item occurred. So perhaps your input was like 12, and then you'd go through your list of items counting the number of 12s, right? So that would require you to go through the entire list, right? So let's say you had a list of 1,000 items. You'd have to compare each of those items to 12 to see if it should be added to the count. So then you'd have to go through 1,000 items if your list was of size 1,000. If you had 1,000,000 items, you'd have to go through all 1,000,000 items looking for the 12, right? So no matter what happens, you have to look at every item in the list, and so it's going to take a time proportional to the size of the list. It's going to take n. But what if you instead had like a search, like a linear search? Then let's say I said, just find me the first 12. Don't count the number of 12s that occur in the list. Just go through all the items, and when you find a 12, stop. Then, if there's no 12s in the list, you'd have to go through every item. But if you found the 12 in the first position, you could just stop. You didn't have to look at the other items. So let's say I had a list of a size 1,000, and I said, find me the first 12, and the 12 was actually the first item. Then I'd find it immediately. It would take a constant time, right? The item would be in the first item, and if it was 1,000 items, it would just take one operation. If I had a list of size 1,000,000 and the 12 was in the first item, it would still only take me one operation. If I had a list of size 1,000,000,000 and the 12 was in the first item, it would still only take me one operation. I just look at the 12 and go, I'm done. Is it fair then to say that algorithm takes a constant time? Well, no, not really. It only takes a constant time if the 12 is in the first item, right? I could just as easily have had a situation where the 12 wasn't even in the list, and then I have to look at the whole list. Okay. In that case, if I had a list of size 1,000, it would take 1,000 operations. And if I had a list of size 1,000,000, it would take 1,000,000 operations. So is it fair to say then that it takes a time proportional to n? No, because sometimes the 12 is in the first item. So what I do is I separate those cases out. I say, well, these different input configurations actually require different analysis. So I'm going to do an entirely separate analysis for these configurations. I split it up into three. One is the best case, which I refer to as B of n. And that's the best configuration that could have happened to our algorithm. That's the configuration of input that makes our algorithm just run super fast as it possibly can. In the case of linear search, that's where the thing I'm searching for is the first item, right? But if you think of, say, binary search looks at the middle item first. So in that case, the best case would be if the key is in the middle item, and it would find it immediately then. I also want to do a worst case analysis, which I refer to as W of n. And that's the worst thing that can happen to our algorithm. That's the bit where we like run our algorithm and we're just like, oh, what is this nonsense? And in the case of linear search, that's when the item is in the last position or isn't even in the list. And that means we have to look at every item to find the one that we're looking for. But, for every algorithm, you end up with a different worst case. The worst case could be anything. And the average case, well, that's a more complicated one. The average case is not the best, not the worst. How does it do on average? How does it do, in general, basically? Let's look at an example of the linear search. I sort of did it in a kind of conversational hand-wavy way, but let's look at it a bit more seriously. So looking at the list that's presented there with the 17, 23, 5, 8, 1, 2, what's the best case? What would I be searching for that would make this thing run the fastest? Hopefully you came up with 17, right? Because if I'm looking for the 17, I'd immediately see 17 and go, okay, I'm done. How long would that take? That would take just one operation. Okay. What's the worst thing? Okay, let's constrain the linear search so that it can only search for things that are in the array, right? So I can't look at that array and say I'm searching for 19 because there's no 19. Okay. So let's say I have to search for an item that's in the list. What's the worst thing I could be searching for? 2, right? This is sounding a bit like Dora the Explorer, where she asks a question and she waits for you to say the answer, and then she goes, bueno. Yes, bueno. The worst thing would be that I'm searching for the 2. And in that case, I'd have to look through every item. So it'd take me 6 operations and I'd find the 2. Okay. For a list of size n, it would take me n operations because I'd have to look through all of them. How long does it take on average? That's a bit more messy. The first thing I want to think about is what does it mean to say that I want to average the performance. Does it mean that I want to take the average over all cases? Or does it mean I want to take the average over all cases that might possibly happen? So sometimes there might be some cases where the algorithm would take forever, but I know that those cases are never going to happen, so I don't want to include them because they're just super unlikely. Well, who knows? That's a parameter that's based on how you want to do the analysis for the decision you have to make. For the case of linear search, we're going to take the average over all possible cases, right? So let's try it. So let's look at an array that just has 2 elements. In this example, there's only 2 possible cases. Either the key is in the first element or it's in the second element, right? If it's in the first element, the algorithm is going to take 1 operation, and if it's in the second element, it's going to take 2 operations. So on average, it's going to take 1.5 operations, right? Which is just 1 plus 2 over 2, just the standard average of the 2 possible cases, of the costs of the 2 possible cases. Let's take an example where there's 3 elements in the array. Well, in this case, there's 3 possible things that could happen. The key could be in the first, second, or third position, and that'll take either 1, 2, or 3 operations respectively. If I average 1, 2, and 3, I get 2, right? 1 plus 2 plus 3 over 3. But the principle here is that what I'm doing in each of these things is I'm just summing up the costs of all possible cases and dividing by the number of cases. Okay, so to get the average cost of every case. So if I had an array of size n, the key could be in the first position, the second position, the third position, all the way up to the nth position, which means it might cost me 1, 2, 3, 4, all the way up to n. Okay, and then I divide by n, which is my number of cases. So I get the expression that's in the first bullet point, 1 plus 2 plus 3 plus ... plus n over n. Okay, which I can rewrite as the sum from I equals 1 to n of I over n. Okay, and I know that the sum of I equals 1 to n of I is n into n plus 1 over 2. That's an arithmetic series. And so that means my whole expression becomes n into n plus 1 over 2 over n, right? So n into n plus 1 over 2 n, which is equal to n plus 1 over 2. So now I've got my function. I've got a function n plus 1 over 2, which represents the average case complexity of the linear search algorithm. Now notice that was a lot harder than the best or worst case analysis, right? In the best and worst case, I could just eyeball it and say, hey, best case, it took 1 because it just looked at the first one. I didn't have to go through all of this math. So the average case in general is a lot harder than the best and worst case. And in this case, I simplified it because I said the item has to be in the list. What would happen if I didn't say that? Well, then the item, I'd have to think about whether the item is in the list. I'd have to think about the probability that it's not in the list and factor that in somehow, and maybe think about characteristics of how I gather my input that might say that the item has a 70% chance of being in the list. And I mean, it would just become a nightmare. So average case is a lot harder than best and worst case, just in general. Now, the important thing to think about here is that these cases deal with different configurations of input. Again, I can't stress enough, you're not allowed to change the size of the input because the graph that I want is a graph of the input size versus the time taken, right? And I don't want that graph because I'm trying to make life difficult. I want that graph because I get to make decisions, right? So when I have that graph and I'm the algorithm designer or the program designer, and I want to pick between various algorithms, I could say, hey, you know what, this algorithm takes 3n plus 4, and this other algorithm takes half n squared. Which one do I want? Well, knowing what the graphs look like, I can say I want the one that takes 3n plus 4. If on the other hand, I constrained my n, if I said the best case is where there's just no items in the list, then I'd say, well, algorithm A takes 0 because there's no items in the list, and algorithm B takes 0 because there's no items in the list. Which one should I choose? Who knows? So I might have cheated by making the analysis a lot easier, but it was a very useless analysis. It didn't let me pick a better algorithm, right? Which is really the point of the exercise. Now, something that people often get confused between is the best, worst, and average case versus the upper bound, lower bound, and exact bounds of the algorithm. Now, I haven't yet talked about what those are, but just keep in mind that when I talk about cases, when I talk about best case, worst case, and average case, I'm always talking about configurations of input, right? If we're not talking about the sort of configurations of input, and then we're not talking about cases, okay? So just keep that in mind. The only thing you get to choose when you're talking about best, worst, and average case is the configuration of the input, not its size, and not some other factors which we'll talk about in the next lecture relating to uncertainty. Okay, thank you for listening. If you guys have any questions, post them to the forums or to the WhatsApp group, and we'll get back to you. Thank you.